Hello. I'm going to be learning Calculus 3 again. It's about I'm still studying the vectors chapter. Wait, let me just change the full screen first. Hold on, I just need to fix a few things. Okay, so last stream I started studying vectors and I did these two chapters, vectors in a plane and vectors in 3 dimension. This stream I would be learning dot product and cross product and maybe I would finish the entire chapter. Hopefully I would finish the entire chapter, but I don't know how much I'm going to do today. Okay, so let's start with this. Also, I was using Desmos. I think GeoGebra is good for vectors. It's like you can make a vector over here like this. Then you can like add a point over here, 1, 1, 1. And then, yeah, they show a vector. And then the other point, uh, 1, 0, 2. Yeah. Uh, Maybe because I'm streaming, it's getting quite slow. But sometimes you can add only the terminal point and then it will show the vector from the origin. Uh, in this section, we develop an operation called the dot product, which allows us to calculate work in the case when the force vector and motion vector have different directions. The dot product essentially tells us how much of the force vector and the motion vector have different directions. The dot product essentially tells us how much of the force vector is applied in the direction of the motion vector. The dot product can also help us measure the angle formed by pairs of vectors and the position of a vector relative to the coordinate axis. Okay, wait, hold on. Let me just open Excalibur as well. Okay. So what happened? Okay. We have already learned how to add and subtract vectors. In this chapter, we investigate two types of vector multiplication. The first type of vector multiplication is called the dot product. Based on the notation we use for it is defined as follows. The dot product of vectors u and v is given by the sum of the products of the components. So u times v is u1 v1 plus u2 v2 plus u3 v3. Uh, Note that if u and v are two-dimensional vectors, we calculate the dot product in a similar fashion. Thus, if u1, u2 and v is v1, v2, then the dot product is u1, v1 plus u2, v2. When two vectors are combined under addition or subtraction, the result is a vector. When two vectors are combined using dot product, the result is a scalar. For this reason, the dot product is often called the scalar product. It may also be called the inner product. Okay. Control Shift S, capture area, copy. Okay, so let's see. So we have 352 and minus 130. So u dot v is, I don't know why it keeps doing this. Uh, this is in 3 dimension. u1 v1 plus u2 v2 plus u3 v3. Okay. u1 v1, so it's 3 times 1 plus it with 5 times 3 plus it with 2 times 0. We get minus 3 plus 15, which gives 12. As for the second part, you have P and Q. And I think the dot product would be 10 times minus 2 plus minus 4 times 1 plus 7 times 6. We have minus 20 minus 4 7 times 6 is 42. Then 42 minus 24 is 18. Twelve and 18. Okay. Is there like a PDF of this? I do control P. Like vector addition and subtraction. I think I would just print this and view the printed version because it keeps on loading. Never mind. Like vector addition and subtraction, the dot product has several algebraic properties. We prove 3 of these properties and leave the rest as exercise. So UV is the same as VU. U times V plus W is the distributive property. And then some scalar C times the dot product of UV. You can do the associative property. And then V times V is magnitude square. Using properties of the dot product, let A, B, and C be these three. Find each of the following. So A, B times C, Control Shift S. Let me just delete that one. So, no, wait, this is the wrong picture. So so the dot product of this is 1 times 0 plus it with 2 times 2 plus it with minus 3 times 4. Which gives you 4 minus 12. And then what is this? I thought that was a scalar. This is a scalar, wait. Oh, I see. Yeah. Now I understand. So C. Also, I've noticed they didn't actually represent this way of representing vectors. 5 minus 1, 3. So then the dot product times vector C gives 40 minus 48 and minus 24. I will just do the first one and only. So minus 48 minus 24. And let's just do the C. So B dot P is 0 times 0, 2 times 2, 4 times 4, 4 plus 16, which is 20, which is magnitude squared. Using the dot product to find the angle between two vectors. Where two non-zero vectors are placed in standard position, whether in 2-dimension or 3-dimension, they form an angle between them. The dot product provides a way to find the measure of this angle. This property is the result of the fact that we can express the dot product in terms of cosine of the angle formed by the two vectors. The dot product of two vectors is the product of the magnitude of each vector and the cosine of the angle between them. So proof: place vectors u and v in standard position and consider vector v minus u. So u, v, and then v minus u. These three vectors form a triangle with side lengths magnitude of u, magnitude of v, and magnitude of v minus u. Recall that from trigonometry, the law of cosine describes the relationship among side lengths of the triangle and the angle theta. Applying the law of cosine here gives, so we have this squared plus this squared plus this squared minus 2uv cos theta. The dot product provides a way to rewrite the left side of this equation as this. Oh yeah, that is the, what's the property called? Property of magnitude. So we can write this like this, and then we can use the other property and end up with this. Substituting in the law of cosine yields. Okay, so this is the law of cosine. And they're substituting this over here. So u and v cancels out. And then minus 2 would cancel out, and then we would be left with this. We can use this form of the dot product to measure the angle, to find the measure of the angle between two non-zero vectors. The following equation rearranges equation 2.3 to solve for the cosine of the angle. Using this equation, we can find the cosine of the angle between two non-zero vectors. Find the measure of the angle between each pair of vectors. Okay, let me just delete. So, what they want is so the equation is that the dot product of u and v is the magnitude of u. It's allowed to write one line, right? Like this is allowed, right? Times the magnitude of v times cos theta. So for A we have let's say u is 111 and let's say v is 2 minus 1 minus 3, and then the magnitude of u is root 1 square plus 1 square plus 1 square which is root 3. The magnitude of V 2 square, which is 4, minus 1 square, which is 1, minus 3 square, which is 9. So root 14. And the dot product is 1 times 2 plus it with, I'll just write, it's just these three, right? So this multiplied by each of this would be the same. So 2 minus 1 minus 3, 2 minus 4 minus 2. So we have minus 2 cos theta. Does GeoGebra have like their own calculator? If I do, does it show? Okay. So we have 2 over root 3 times 14, 0.13, and then cos 0.31 is 71.94 degrees. Let's just do the first one. Hold on. I mean, they got this. They say minus 2. Why is it? Oh, yeah, it's minus 2. Should be minus. So 108 degrees. The angle between the two vectors can be acute, obtuse, or straight. If cos theta is 1, then both vectors have the same direction. If cos theta is 0, then the vectors, when placed in standard position, form a right angle. Okay. So an obtuse angle, an acute angle at A, and then C is a straight line. Cos theta is minus 1. Here cos theta is 1. Then here cos theta is 0. The non-zero vectors u and v are orthogonal vectors if and only if u dot v is 0. Let u and v be non-zero vectors. The terms orthogonal, perpendicular, and normal each indicate the mathematical objects are intersecting at right angles. Okay, let u, okay, so they're at right angle if the dot product is 0. So let u and v be non-zero vectors and let theta denote the angle between them. First assume u dot v is 0. Then we get this. So first we start with their dot product being 0. We get this. And let's assume u and v are non-zero, so they will have a magnitude. So we must have cos theta is 0. Hence theta is 90. Therefore, the vectors are orthogonal. Now assume that the vectors are orthogonal, then theta would be 90, and then we would have u dot v is 0. Identifying orthogonal vectors. Determine whether these two are orthogonal. We'd have 1 times 10, 0 times 3, and 5 times minus 2. So 0 times 3 would be 0, 1 times 10 would be 10, and 5 times minus 2 would be minus 10. So they would cancel out and give 0. So that means they're orthogonal. Measuring the angle formed by two vectors. Let V be 2, 3, 3. Find the measure of angles formed by the following vectors, V and I. So we have oh no, not this. Copy. Okay. Let's just delete this picture. So we have V 2, 3, 3. And then we have I J and then K. So magnitude of V. Each of these magnitude is 1. Magnitude of V is 2 square, which is 4 plus 9 plus 9. So we have 18 plus 4, right? And then we have V dot I is equal to just 2 because 3 times 0, 3 times 0. So we are left with 2. Also V dot J is 3. And then V dot K is 3. So we have this. So cos theta. So we are left with 2 over root 22. Theta. Let's call it theta I. We have 2 over root 22, 64.76 degrees. Can we convert it to radians? How do I convert this to radians? I don't know. Anyways, it's 64.76 degrees. Yeah, they got arc cos 2 over root 22. Well, I only measured the angle between I, but for Jane, it's the same process. The angles formed by a non-zero vector and coordinate axis are called the direction angles for the vectors. The cosine for these angles are called direction cosine. The direction cosines of V233 are cos alpha 2 over root 22, cos beta 3 over root 22, and cos, what is this? This is gamma 3 over root 22. The direction angle are these radians. As we have seen, addition combines two vectors to create a resultant vector. But what if we are given a vector and we need to find its component parts? We use vector projection to form the opposite process. We can break down a vector into its components. The magnitude of a vector projection is a scalar projection. For example, if a child is pulling the handle of a wagon at 55 degrees angle, we can use projections to determine how much of the force on the handle is actually moving the wagon forward. We return to this example and learn how to solve it after we see how to calculate projections. The vector projection of V onto U is labeled projection V on U. Or it's the notation projection of V on U. It has the same initial point as UV and the direction in the same direction as U, and represents the components of V that acts in the direction of U. Theta represents the angle between U and V. Then by properties of triangles, we know the length of projection V is magnitude of projection V, which is magnitude of V cos theta. Oh, so this force here, they want to know what's the force in the horizontal direction. So you just do F cos 55 to get the force in this direction. So we have this. So projection is V cos theta, magnitude of V cos theta. Cos theta can be represented like this. Then this and this cancel out. So we are left with the dot product divided by the magnitude of U. Wait, hold on. If I go back to the dot product, why is it like modulus over here? There's some modulus here. We now multiply by a unit vector in the direction of U to get projection V. Okay. Yeah, I think I understand. The length of this vector is also known as a scalar projection of V onto U and is denoted by this. What's the difference between these two? This is a vector. This is the scalar, right? Okay, let's try an exercise. But I still don't understand where the modulus is coming from. So we have theta v u. We have projection, which we will just call p, of v onto u. The magnitude, the length of this projection is the length of v. I think I will use double line to represent the magnitude of vector and then single line to represent modulus. We have this cos theta. According to the dot product, we have magnitude of v times it by magnitude of u cos theta so cos theta is hold on, no wait, I don't think this is correct, because if it's like this, theta is really big, like more than 90 big. We have this projection is over here. Projection is a vector, right? Yeah, wait, I don't know why this is not loading. So yeah, projection is this. So cos theta is v u, the magnitude of v times it by the magnitude of u. Then if we place it over here, we get p. The v will cancel out, and then we will be left with v dot u over magnitude of u. This is it, right? I don't know where the modulus is coming from. Why are they multiplying it by a unit vector in the direction of u? I think there may have been some mistake in the There may have been some mistake here. Let me just see how they solve this. Find the projection of V onto U. So we have this, right? What is this? I don't know why this is so slow. So we have example 2.27. Projection of V on the direction of U. We have V dot U, the magnitude of U. Magnitude of U is 1 plus 16 plus 9, which is root 26. And then this gives us scalar, right? V dot U would give 3 times minus 1, which is just minus 3. Plus it by 5 times 4 is 20 plus 3, which is just 20. So this here is equal to 20 over root 26. Wait, 20 over root 26. No, wait, I think I'm wrong here. The magnitude of the projection is given by this. Then we are left with the magnitude of the projection. But we don't know which direction it's facing. It's facing either this direction or that direction. That's why we need to multiply by the unit vector of U. Hold on. Think I understand now. So we take this. We got 20 over 26. And then we multiplied by minus 143. We got minus 1 over root 26. And then 4 over root 26. 3 over root 26. Which gives us 20 over 26. And then 80 over 26. Then 60 over 26. Yeah, this is the simplified version. Okay, I think I understand now. I think this part confused me. This should be the magnitude of the projection. Sometimes it is useful to decompose vectors, that is, to break a vector apart into a sum. This process is called the resolution of a vector into components. Projections allow us to identify two orthogonal vectors having a desired sum. For example, let V be 6 and minus 4 and let U be 3 and 1, and decompose the vectors V into orthogonal components such that one component vector has the same direction as U. Now consider the vector Q is equal to V minus P. So we have V and then minus P, which would give us this part. Oh, so that's the orthogonal part. V minus V. Clearly, by way we define Q, we have V is equal to Q plus P, and Q dot P is 0. Therefore, Q and P are orthogonal. Resolving vectors into components. Express V, which is 8 minus 3 as a sum of orthogonal vectors such that one of the vectors has the same direction as U. Okay, I think I'm trying to understand now. So, copy, copy again. This is 2.28. So, express V 8 minus 3 and minus 3 as the sum of orthogonal vectors such that one of the vectors has the same direction as U. So, let's say projection P is projection of V onto U. Then the magnitude of P is V U over this, and then U is 2 square, so 2 square plus 3 square plus 2 square, 4 plus 4, and then 3 square is 9. Root 17. And then if we do U, we get uh, 2 root 17. This is the unit vector in the direction of U. And then the dot product of V and U is 8 times 2, 16. 3 times minus 3 is 9. Minus 3 times 2 is minus 6. I have a calculator next to me. 16. This is 1. So this over here is 1 over root 17. And then P as a vector is its magnitude times the direction. Three. Is it 232? Yeah. So we have 2 over root 17. Then we get 2 over 17, 3 over 17, and then 2 over 17 again. So this is P. Then Q is like, Q is V minus P, right? V minus P, which is 8 minus 3 minus 3. Then 2 over 17 subtracted by 2 over root 17 minus 3 over 17 minus it with 2 over 17. And whatever the evaluation of this is. Let's see the answer. Okay, so Q is this. P is, yeah, that's correct. Okay, so this doesn't work. Okay, this, that one. Hold on. I should just get a PDF of these. I think they do provide PDFs. So a container ship leaves port traveling 15 degrees north of east. Its engine generates a speed of 20 knots along that path. In addition, the ocean current moves the ship northeast at the speed of 2 knots. Consider both the engine and the current. How fast is the ship moving in the direction 15 degrees north of east? Round the answer to 2 decimal places. So we have, hold on, let me just remove this. We have a ship container leaves port traveling 15 degrees, so the velocity is that way. Its engine generates a speed of 20 knots. So we have this, we have this, and then we have so V, which is 20, I'll just write K, 20 knots. And then in addition, the ocean current moves the ship northeast at a speed of 2 knots. Is that W? So V is this. Consider both the engine and the current. How fast is the ship moving in the direction 15 degrees? How fast is the ship moving in the direction 15 degrees north of east? Round the answer to 2 decimal places. So what is this W over here? The ocean current moves the ship northeast, or this is northeast, at a speed of 2 knots. So 2K, and this is W. And then this is 15, and this is 45. It doesn't look like 45, but let's just pretend it's 45. So 2 knots, 20 knots, and we want to see how fast is the ship moving in this direction. So they want this direction. So it's basically 20 knots plus the projection of this in this direction. So we have P is the projection of W on V. So P is equal to, actually the magnitude of P is the magnitude of W cos theta. So wait a minute, but we know what's cos theta. It's 45 minus 15. The magnitude of W is 2. So 2 times it by cos 45 minus 15, which is 30. Which is around, I'll just use a calculator with me, which is equal to root 3. But we need this. We have the scalar, we need it in the direction of V. No, actually we just need this. So root 3. Hold on. It's just root 3 plus 20, right? So root 3 in this direction. Root 3 plus 20. Isn't that the answer? Yeah. times it by, no, plus 121.73 knots in the v direction. Now that we understand dot products, we can see how to apply them in real life situations. The most common application of dot product of two vectors is in calculation of work. From physics, we know that work is done when an object is moved by a force. When the force is constant and applied in the same direction the object moves, then we define the work done as the product of the force and the distance the object travels. So work is force times distance. We saw several examples of this type in earlier chapters. Now imagine the direction of force is different from the direction of motion, as with the child pulling the wagon. To find the work done, we need to multiply the components of the force that acts in the direction of the motion by the magnitude of the displacement. Okay. When a constant force is applied to an object, so the object moves in a straight line from point P to point Q. The object moves from P to Q in a straight line. The work W done by the force F acting at an angle theta from the line of motion is given by this. So work is it's in this direction, right? Actually, the dot product also gives hold on. Work done is given by this. So the magnitude of PQ times by the magnitude of F cos theta. So it's the magnitude of the work in this direction. Yeah, I should just go to the next chapter. And the cross product. This material uses a 3 times 3 determinant of the form ABC, oh my God, which expands by minors to this. In this section, we develop an operation called the cross product, which allows us to find a vector orthogonal to two given vectors, calculating the torque in an important application of cross products. And we examine the torque in more detail later in this section. The cross product and its properties. The dot product is the multiplication of two vectors that results in a scalar. In this section, we introduce a product of two vectors that generates a third vector orthogonal to the first two. Consider how we might find such a vector. Let u be this and v be this, be non-zero vectors. We want to find w orthogonal to both u and v. That is, we want to find w such that u dot v is 0. So, I mean, u dot w is 0 and v dot w is 0. Therefore, so both of these must satisfy. If we multiply the top equation by v3, the bottom equation by u3 and subtract, we can eliminate the variables w3, which gives us this. Oh, so they did. What did they do? So they multiplied v3 on both sides. Yeah, they multiplied v3 over here and they multiplied u3 over here. and then they got this. And these two cancelled out. If we select V1 as this and W1 as this and W2 as this, we get a possible solution vector. Substituting these values back to the original equation gives this. But wait a minute. They're finding a vector that's orthogonal to the two vectors, right? But isn't there two directions of this? Like, let's say there's a vector here, a vector here, the red vector and the blue vector. Then the green vector can have two directions, right? That is vector W is this. So W1 is this, W2 is this. And W3 is this. This is orthogonal to both U and V, but in which direction though? Which leads us to define the following operation called the cross product. Cross product is U2 V3 U2 V3 minus V3 U2 V3 minus U3 V2 U2 V3. So in this direction, so if you want to find the first value, we do what's happening, U2 V3 minus U3 V2. Why is it stuck? Now for the second component, we do U1 V3 minus U3 V1. For the third component, we find U1 V2 then U2 minus U2 V1. From the way we have developed U times V, it should be clear that the cross product is orthogonal to both U and V. However, it never hurts to check to show that U cross V is orthogonal to U. We calculate the dot product of U and U times V, and they get 0. Okay, so let's find the cross product. Example 2.31. Example why does it keep doing this? P is minus 1 to 5. Okay. So P is minus 1 to 5. I don't know why it keeps getting stuck. I'm thinking like next stream I might get the PDFs of these because that is slightly faster. Negative 1 to 5, 4 0 minus 3. 4 for 0 minus 3. So for the cross product, let's do short here. For the cross product, we have, so this times this minus this times this. So 2 times minus 3. Wait. Minus it with 5 times 0. That's the first component. And then for the second component, we have minus 1 times minus 3. Minus it with 5 times 4. For the third component, we have minus 1 times 0. Times it by 2 times 4. So 2 times 3 is minus 6. Minus 1 times minus 3 is 3. 3 minus 20 is minus 17. And then 2 times 4 is 8. So minus 6, 17, and minus 8. Why is it 17? Minus 6, 17, and minus 8. They did minus 1 times minus 3. Minus it with 5 times 4. Maybe I copied the question wrong. No. Okay, let's see. 2 times minus 3. Minus it with 5 times 0. And then for the third one, minus 1 times 0. Minus it with 2 times 4. And then for the second one, it should be minus 1 times minus 3. I think they did a mistake here. Or maybe I did a mistake here. The cross product is negative for the second one. So plus and minus. Although it may not be obvious from equation 2.9, the direction of u cross v is given by the right hand rule. We hold our right hand with the finger pointing in the direction of u, then curl our finger towards v. So u and then curl finger towards v. This is the direction of u cross v. Notice what this means for the direction of V cross U. If we apply the right hand rule to V cross U, we start with our fingers pointed in the direction of V, then curl our fingers towards the vector U. In this case, the thumb points in the opposite direction of V, U times V. Anti-commutativity of the cross product. So U and V and V and U gives different products. They just face in the opposite direction, right? Yeah. The cross products of the standard unit vectors I, j, k can be useful for simplifying some calculations. So let's consider these cross products. A straightforward application of the definition shows that I cross product I, j cross product j, all of them give 0. The cross product is of two vectors as a vector, so each vector of these products results in a 0 vector, not a scalar 0. Because the cross product of two vectors is orthogonal to each of these vectors, we know that the cross product of I and j is parallel to k. Similarly, the vector product of I and k is parallel to j, and the vector product of j and k is parallel to I. We can use the right hand rule to determine the direction of each product. So cross product of standard unit vectors j cross product I and j cross product k, j cross product k gives I, and I cross I gives 0. Okay, so the properties are cross product is sometimes called a vector product. So the properties are u cross v is minus v cross u cross v plus w is u cross v plus u cross w. Then multiplying them by a constant gives cu cross v. This time the constant only applies to one of them. Then you have 0, and then we have v cross v gives 0. And then the dot product. Wait, hold on. So u dot v cross w is u cross v dot w. Okay, the cross product can be quite confusing. Let u and v be vectors and let theta be the angle between them. So we have this. Hold on. U cross v is the magnitude of u cross v is magnitude of u times dot magnitude of v times pi sine theta. Use the properties of cross product to find the magnitude of the cross product u and v. So we have 0 for 0 and 0 0 minus 3. Zero for 0 and then 0 0 minus 3. And then we have magnitude is root 4 square, which is just 4. Magnitude of V is 3. So this, we have this, and we have these three are orthogonal, right? So sine, which is just 4 times 3 is 12. We can calculate the cross product of two vectors using determinant notation. A2 times 2 determinant is defined by this. So this is A1, B2 minus set with. It would have made more sense if they defined it like column wise. Okay, so A1 minus B2 and B1 minus A. Okay. A 3 times 3 determinant is defined in terms of 2 times 2 determinants as follows. So A1, the determinant of this, A2 and the determinant of this, and then A3 minus A2 determinant of this, and then plus A3 times the determinant of the first box. So example 2.36. Two, 5 minus 1. And then we have minus 2, 3, 4. Two, 5 minus 1, minus 1, 1, 3, and then minus 2, 3, 4. Okay, so we have this is equal to 2 times this box over here. Minus it with 5 times the box formed by these. And then plus it with minus 1 times it by box formed by these. And then we have 2 times it by 1 times 4. I think it's minus, right? Yeah, minus. So 1 times 4 is 4. Minus 9, so plus 9. And then we have minus 5 Minus 1 times 4 is minus 4. Then we have minus 2 times minus 3, which is 6. And then we have minus 3 minus 2. Like that. So we have 2 times 13, which is 26. Minus it with minus 4 minus 6 is minus 10. 5, and this will be plus 10. And then this would be plus 1. This would be 37. I got it wrong. It's minus 19. So where did I get this wrong? Or is it supposed to be minus 9? So 1 times 4 minus 3 times minus 3. Hold on. Did I copy it wrong? I think I copied it wrong. This is 3. This is 3. And this is 3. So this would be minus 9. 3 times 2 is 6. So we have minus 6. So this becomes plus, right? Hold on. Minus 1 times 4 is plus 6. Oh, even this is wrong. And then we are left with, I mean, in the previous calculation, this 10 was wrong. It was supposed to be 50, I think. Plus 10, this is supposed to be 10. And then we are left with 10, 10, 1, minus 10, minus 10, 1. How minus 10? Okay, so this I can understand. How is this minus 10? So 6. Yeah, it's minus 10. And then we are left with minus 19. Cross product calculated by determinant. Let U be this and V be this. The cross product U cross V is given by this. Yeah, I don't want to do all that again. Finding a unit vector orthogonal to two given vectors. Okay, so hold on. Copy, paste. That's the wrong picture. Copy, paste. Again, it's the wrong picture. Why does it do this? I think I should wait a while. copy, right? And then I should paste. Yeah. Find a unit vector orthogonal to both A and B. So if we have the determinant of I, J, K, 5, 2, -1, 0, -1, 4. Then we have I, determinant of this box. And then we have -J, determinant of these two. Plus it with K. Determinant of 5, 2, 0, -1. So this is I times it by 2 times 4, which is 8, -1. And then -J is 5 times 4 is 20, minus -1, just +1. I'll just write 21 here. Plus it with K. -5, -2. And this gives 8 minus 1 is 7, -21, -5 minus 2 is -7. And if, like, let's call this V. Magnitude of V is 7 square plus 7 square, 2 times 7 square, plus 21 square. I have a calculator with me. √11. So 1 over √11 minus 3 over √11 minus 1 over √11. Is this the correct answer? I got it wrong. So I'm -7. Oh wait, I forgot. This is 5. -5. And then this would be 5 square. 7 square plus 5 square plus 21 square. Is that correct? Why is it 20? Minus 1, minus, minus 1. No, wait. Minus 1 times minus 1. Why did I do this? 20. So using a calculator again. Root 4. 474. And then, yeah. If we locate V and U such that they form adjacent sides of a parallelogram, then the area of the parallelogram is given by uh, magnitude of U times magnitude of V. So the magnitude of VU. Hold on. Wait a minute. Magnitude of V, magnitude of U. The area is given by, yeah, this. U, the base times height, times it by magnitude of V sine theta. All of this is the magnitude of the cross product. Wait, how are they doing this? One is here, one is here. Wait a minute. This is, it's a right angle triangle, right? No, 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 not right angle, like an equilateral triangle, because all sides are the same length. So we can use like Pythagorean theorem to find the length of this. That would be the length of all the sides. Then we can use Pythagorean theorem again to find the height. Then we can do half times space times height. We don't really need the cross product. But what are they doing? So P to Q, the vector P to Q, okay. And then they're finding, I think, and then the vector P to R. And they're finding the area of the parallelogram. It's like P to R, like this, the area of the square formed by two of these triangles. And then they're dividing it by 2. I think that's what they're doing, yeah. The triple scalar product of V, U, V, and W is U dot V cross W. So we have okay. It is so lengthy though. Like simple questions take a long time to solve. Okay, so for calculating this, we just need to do this, right? And I've done this before. So U times the determinant of this, U2 times the determinant of the box of these two, then u3 times the box of these four. When we create a matrix from these vectors, we must be careful about the order in which we list the vectors. If we list them in a matrix in one order and then rearrange the rows, the absolute value of the determinant remains unchanged. However, each time two rows switch places, the determinant changes sign. Okay. Volume of a parallel. How do you pronounce this? The volume of this shape with adjacent edges given by vector v, u, and w is the absolute value of the triple scalar product. So v dot v cross u. Oh, because v cross u gives the area of the parallelogram over here. But then what does u dot give? Oh, it gives, yeah. So v cross w also gives this, right? Hmm. Okay, I think I understand. So v cross w gives this, and then if you do u dot this, we get a projection of u over here. But that doesn't give the volume though. Okay, so the volume is this parallelogram times it by the height, which is the projection of u onto v cross w. And I guess they simplified it to this. Okay. Application of cross product. The cross product appears in many practical applications of mathematics, physics, and engineering. Let's examine some of these applications here. Use a triple scalar product to show that these vectors are collinear. Finding the orthogonal vector. Torque measures the tendency of a force to produce rotation about an axis of rotation. Let R be a vector with an initial point located on the axis of rotation, with the terminal point located at the point where the force is applied. Let F represent the force. So force over here, R is the location from the axis. The force is here. The torque is equal to the cross product of R and F. Okay, let's do this exercise. Copy it. And this is what? Exercise 2.41. And So we have V, U, and then W. So we do V cross U, then U dot product with that. U dot product. Magnitude of V cross U, right? No, it's just V cross U. V cross W. So if we have I, J, K, 4, 3, 2, 0, minus 5, minus 2, this gives I 3 times minus 2 is minus 6. Minus it with 5 times 2 is 10. And then we do minus J. 4 times minus 2 is minus 8. Minus it with 0. So that is 4 times 5 is minus 20. And then that's it. And then we have, putting it all together, minus 16, 8, and minus 20. And then we have U dot this, right? U is minus 1, minus 2, 1. So this gives this times this plus this times this plus this times this. So we have 16 plus, or actually minus 8 times 2 is 16, minus 20. And wait, we do like this, we get 20. Nope, it's a minus 40. So where did I make a mistake? So 6 plus 10. Why is it plus 10? So for I, 3 times minus 2, minus it with 5 times 2 is 10. Oh, yeah, this was a mistake. And then so we have 4 over here, and then 4 minus 1, which gives you minus 4. Minus 4, minus 16, minus, okay, that gives minus 40. Wait a minute, plus 40 units squared. A bolt tightened by applying a force of 6 newtons to a 0.5 meter wrench, 0.15 meter wrench. The angle between the wrench and the force is 40 degrees. The force is applied directly upwards by the magnitude of the torque about the center of the bolt. Round the answer to 2 decimal places. So we have 6, 40 and 0.15 meter. The torque is R cross product F, right? Example 2.44. This is 6 newtons. And we have radius of 0.15. And then this is 40 degrees. So if we do F cross R, we get, wait a minute. If we just want to find the magnitude, is there a simpler way? What was that sine theta thing we saw earlier? That's the area of a parallelogram. Magnitude of this. Okay. So, magnitude of this is magnitude of F times it by magnitude of R sine 40. Wait a minute. How did they prove this? Yeah, it was over here. Yeah, they proved it over here. Anyways, so 6 times 0.15 and then sine 40 0.642 This gives 0.579 Newton meter. Wait, let me think. The force is here. So force sine theta would give this, right? So this is calculating actually how much of this force is applied at this point. So it's like this times this. Let's go back. 0.58 Newton meter. Good. Should I do another? I might do it now or maybe in extreme. Is this chapter and the next one related? Okay, maybe I will just do this next stream then. Okay, I will end the stream here. And I'll see you guys next time.